Hello everyone and welcome to another Würth Electronic webinar. My name is Markus Eberle and I will moderate this webinar today. We are very pleased that you took the time today to be in our webinar. So the topic of today's webinar is the effects of harsh environmental conditions on film capacitors. Yes, our speaker today is John Isque Rodriguez, who is working as hardware engineer in the field of capacitors and resistors at Würth Electronic. He will hold today's webinar and also answer your questions in the question answer session after the presentation. Yeah, just said that. So just the information for you, you are muted during the webinar. That means that you cannot ask us questions via the microphone. Nevertheless, you have the opportunity to ask us questions with the chat function. And yeah, after the presentation, which will be about 30 minutes long, we will start into a question and answer session, and we have scheduled for this 10 to 15 minutes in addition of the time. And yeah, if we don't have the time to answer your questions in this live webinar, we will answer it later on via email. And if you afterwards have any questions left, you can just email us at webinarteam@we-online.com. You will also receive the link to the presentation as well as to the recording of this webinar after the webinar and only in the next few days. But now I just want to hand over to our speaker, John, and I wish you an exciting and interesting webinar.
Okay, thanks. Thanks, Marcus. Hi, hello again. Yeah, this is John. I have been working as a hardware engineer in Berlin since 2018 in the capacitor team. And yeah, let's start. As Marcus said, the title of the presentation is the effects of harsh environmental conditions on film capacitors. And wait a moment. And yeah, so in one moment. In this webinar, we will see three main aspects. First, we will see how temperature and humidity conditions affect the different capacitor technologies in a short overview. Then we will focus on film capacitors in more detail and see the different capacitor types in some of the applications. With that in mind, we will see what happens in harsh conditions in those applications. In our case, we are speaking of temperature and humidity conditions because this is the conditions that affect most commonly to capacitors. When we speak of harsh temperature, we are thinking on extremely low or high temperatures, close to the operation limits. Also, thermal shock or repetitive temperature cycles can damage capacitors. Looking at humidity, it only affects film capacitors significantly, which is the focus of this seminar. Of course, in the wider electronic fields, there are other environmental factors like dust, altitude, air pressure, or mechanical shock, vibration, noise, and more. Well, today we will focus on temperature and humidity because that's too much to handle. Let's start with the common ceramic capacitors. The electrical and thermal performance is defined by the used ceramic material. We use two main classes of materials. The MLCCs with class 1 materials have a very stable characteristic in the whole temperature range and have extremely low loss. Class 2 materials, on the other hand, have a dielectric constant much larger, so we get higher capacitance values, but they suffer from voltage and temperature dependencies as well as aging. Class 2 materials are actually classified by the thermal performance of the component. So as specified by the AIA coding that you can see in the slide, you can see that the very common specification X even R, which means a temperature of -55 degrees to 125 degrees maximum, as well as a permitted capacitance deviation of plus minus 15% in that range. In the right, you can see some capacitance deviation of several X even R capacitors of 100 volt voltage rating. Another important thing about MSDCs is the Curie temperature. At this temperature and higher, the material structure change and the capacitance drops significantly. This temperature is different for each material. For example, it is around 130 degrees Celsius for X even R capacitors, which provides the upper limit of operation of 125 degrees. Now, if we look at electrolytic capacitors, there is a lot to talk about. In general, aluminum electrolytic capacitors with a wet electrolyte perform quite bad at very low temperature, and it may even freeze. That is why we have parts with different lower temperature ratings, from minus 25 degrees down to minus 55 degrees. These kind of capacitors actually perform very good in high temperatures with the lower losses. But the problem is that the electrolytic will dry faster from the heat and dry air, so the expected lifetime will be very short. In this diagram, you can see an estimation of the expected lifetime of different series rated for higher temperature. So operating lower and lower from the maximal temperature, the expected lifetime increase exponentially. Polymer parts are plotted in gray, and you can notice the exponential growth is even faster. So you can see the effect of the solid electrolyte for the expected lifetime. Here you can see the results of some measurements at different temperatures. There is a lot to unpack here. In the left side, we have 3 different aluminum electrolytic capacitors of the 3 mounting types that we offer. Red for regular through-hole, the THT component, gray for the snap-ins, and blue for the SMD types, V-chip types. As you can see, capacitance drop significantly in temperatures under zero. But more important, the ESR increase makes them very unpractical in that range. On the other hand, they show very promising characteristic at high temperature, especially the decrease of ESR. Sadly, the electrolytic will dry faster at the higher the temperature. So we can only recommend to drive these capacitors in the coolest possible. Sorry. In the right side, similar measurement with aluminum polymer capacitors. The H-chip SMD types have a very different construction. That is the reason for the very different characteristics. As you can see, polymer capacitors will work perfectly fine at very low temperatures. At high temperatures, the performance may be much worse because of the increase in ESR. But the components will handle the exposure to high temperature much better because of the solid electrolyte will not dry. Finally, supercapacitors of the electric double layer technology have similar temperature curves. The ESR also lowers at high temperature, increasing performance. Sadly, supercapacitors have a very limited temperature range because the combination of full rated voltage and high temperature will lead to a very short expected lifetime. Also, it is possible to drive them at higher temperature, but only reducing the operating voltage. For example, you can see here that even if normally rated voltage is 2.7 volt at 65 degree, we can go up to 85 degree if we reduce the voltage rating to 2.3 volt. In this case, we consider end of the lifetime to be when the capacitance has dropped to 30% of the original value. We have developed a model to calculate supercapacitor lifetime with different loads. If you want more information, please contact us. Now we will focus on the film capacitors, and we will get a little bit into detail in the performance and the application. So the construction of film capacitors is very simple. 2 electrode films with some kind of isolation, like dielectric between and rolled together. some kind of pin or external connection will be soldered to each electrode. The electrodes can be made of metal film or even a metallization layer on the dielectric. And the dielectric material may be paper or also commonly now plastic film. In our case, we will only speak about the metallized plastic film types. Regarding the finalized assembly capacitor, there are many shapes and construction types. We will focus on THT through-hole type of film capacitors, which are encased in a plastic box and filled with epoxy resin. As you can see in the picture in the right, this is the type of capacitors we have in the portfolio for now. This is the temperature specification of a X2 film capacitor, as stated in the datasheet of FTXX. As we saw before, this is a polypropylene film capacitor. The operation temperature range is -50 degrees up to 105 degrees Celsius. Of course, it may be different from other materials. For some components, there is a derating of DC voltage rating at high temperatures, as you can see in the curve in the right side. As always, I encourage that you read all pages of the datasheet before you miss information like this. Now let's see the temperature dependencies of capacitance and dissipation factor in film capacitors. Going over 110 degrees Celsius will irreversibly damage the polypropylene capacitors. And that is the reason why SMD film capacitors are not very common and present many challenges during circuit assembly and solder process. So, excuse me. So we measure capacitors of all our families, film capacitor families, and plotted capacitance drift versus temperature and dissipation factor versus frequency versus at a fixed frequency versus temperature. Now, especially in the left graph, you can see a clear pattern. Clearly, the performance depends entirely on the film dielectric material. So polypropylene is very stable in the whole temperature range. Looking at polyester film capacitors, we can see they have a worse performance at very high and very low temperatures. This is why the specified maximum performance is actually, specified maximum temperature is actually 85 degrees Celsius for our FTBE film capacitors with polyester film. Now, let's look at some film capacitor applications. One widely used application for film capacitors is the filter at the mains voltage power lines. These capacitors fulfill two main functions regarding EMC regulation, as defined by the IEC standard 60384, to suppress conducted interference and also to protect the application from voltage surge in the power lines. There are two possible connecting positions, depending on which the capacitor will be called X or Y capacitors. The X capacitor is connected between the power lines, also called across the line or parallel to mains voltage. The idea is to filter out the interference from and to the application, as defined in the EMC regulation. Also, each capacitor will be able to absorb and survive voltage surge from the power lines, and also protect the application, as well as self-heal and keep working as a capacitor afterwards. Y capacitors, on the other hand, are connected between each power line and the protective ground or chassis. They are explicitly designed to fail open, to protect human from electric shock. They also filter noise to ground, especially common mode noise affecting both power lines. They are also designed to withstand higher voltage surge than X capacitors. Of course, if we have two Y capacitors, they will also act like one smaller X capacitor, but the opposite is not true. We can never use X capacitors in the Y position because of the open failure criteria. So as we saw before, the X and Y define the position of the connection in the mains power lines. Then there is the number that represents the surge voltage capabilities. So for example, is 2 caps are certified to be able to withstand a defined pulse of 2.5 kilovolt. And then the self-healing process will fill the gap, and the capacitor will keep working with some capacitance drop. Why capacitors start from a higher ruggedness to surge voltage? X2 and Y2 capacitors are used in the mains power appliance in general, while X1 and Y1 capacitors may be used in industrial devices or other equipment connected through three-phase lines or higher voltage. That is why the voltage requirements are also higher. There is another interesting application for X2 capacitors. There is a AC/DC power supply topology called capacitive power supply or transformerless power supply. It works just placing a capacitor in series with a rectifier, so that the capacitor acts as a AC voltage divider, as a main voltage dropper. There are some reasons to have some inefficient components like a resistor in series. So this converter topology is not very efficient, but it is interesting in the very low power range, up to a few watts, because it's very simple and has a very low part cost. Normally, X2 capacitors are used here because what the input capacitor is seeing is actually almost the same voltage as in the X placement. But interestingly, we can see in many datasheets that they explicitly forbid the use of X2 capacitors in such applications. Sometimes you can see this in the datasheet as not recommended for series to mains applications. Another huge application for free capacitors is the use as so-called DC link capacitors. DC link capacitors are needed to decouple the power bridge stage of inverters from the DC source. Specifically, build capacitors are made mostly with polypropylene film and are rated for very high currents. We are planning the release later this year in 2022, as a product series called CAP FTDB with capacitance range between 1 and 75 microfarad and a voltage up to 1,200 volts. Another application of field capacitors are resonant tanks and LNC circuits. Resonant tanks require very stable capacitance values because the use frequency depends on both self-inductance and capacitance, so it should not vary over time. In the left, you can see an example of a DC-DC converter with a topology called LLC, a resonant converter. This is basically the opposite of the previous slide. First the inverter and then the rectifier. In the right, you can see an example of a resonating circuit of the wireless power transfer. The transfer is happening through inductive coupling like a transformer. So of course, this is an AC circuit. Maybe you have heard before of THV capacitors. So what does THV even mean? THV means temperature humidity bias. These swing capacitors are especially built for harsh conditions. In the picture, you can see a section of their datasheet of our Fuji family of X2 THV capacitors. The normal X2 requirements are here, but also the heat dump test is described as defined by the standard EEC 60384 section 14. This is the 85 degrees Celsius with 85% relative humidity, all while loaded with the rated AC voltage of 310 volt RMS. This test is informally called the 85-85 test, and normally it takes 1,000 hours. If it is passed, sometimes the parts are given a so-called environmental grade 3B, as defined by the same standard. Excuse me. Taking into account to reach the 85% humidity, at least temperature at this temperature there is a huge amount of water in the air. For reference, you have this table with some common conditions used in datasheets. First one is considered ideal laboratory conditions at 20 degrees Celsius and 35% humidity. We only have 6 grams of water in a cubic meter of air. But in 85 test, there is almost 50 times more water in the air. I want to show you the measurement setup for this kind of test. This is one of our climatic chambers in our office in Berlin. It's a very versatile and powerful chamber. The cabinet volume is 110 liter, and the temperature range is from -70 to 180 degree, with a maximum humidity of 95%. To multiply the measurement possibilities of our calibrated LCR meter, I designed and programmed the modular multi-switch system that you can see in the image. I can control it as a USB device and switch between several duties, thanks to the relay boards that you can see in the middle picture. So we start the next section and we see what actually happens with field capacitors at high temperature and high humidity, like in the sauna. This is just a small joke, but you can see the THV capacitor is not having a bad time. By the way, if you want to measure temperature and humidity, check out our VWSANTIDS temperature sensor IC and the series HIDS the humidity sensor ICs with integrated temperature sensor. Check that out in our online catalog. So we performed the 85 test with 1000 hours with the mains voltage load of around 230 volt. This was the mains voltage from our headquarters laboratory. So lots of variation during the 42 something days happened, as well as voltage transients. To see the effect of each factor, we connected some components also at the room temperature outside of the climate chamber. And also some parts inside of the chamber were not connected to any voltage. As you can see, the combination of harsh conditions and low voltage damaged the components. We were happy to find out that the components could handle the harsh environment when they had no voltage. We were also pleased to see that the THV parts did not suffer any significant degradation, even after a harsh test. Here we represent the same result from the 85 load test, and we compare our parts with 3 competitors. As you can see, the results are very varied. Competitor A performed well with the regular and THV components, but competitor B did have more robust regular X capacitors. Competitor C, on the other hand, they did not offer THV parts, but the normal parts did actually perform better than any of the regular normal capacitors. Here is another way of representing the result, like the performance of an arbitrary lane filter. We measure the frequency response of a filter with the components before the heat dump test and after. In pink, you can see the normal curve as well as the one with the capacitor, which was at room temperature. The blue one was in the climate chamber but had no load voltage, so no real difference in the filter performance. The green and yellow components that did the loaded heat dump test, you can see the effect of the capacitance drop. The desired damping of frequency higher than 10 kilohertz is gone. So the filtering functionality of the capacitor is completely compromised. What is happening inside the capacitor? There are many mechanisms that cause a reduction in the metallized surface. In the end, because the electrode surface is smaller, the capacitance drops. The electrochemical corrosion is driven by the combination of voltage and humidity. Due to imperfect sealing, water vapor will permeate and cause corrosion, which will appear in the dielectric as spots. This is the main phenomenon affecting the capacitors during heat dump test. There is also self-healing damage, which will appear when the capacitor is absorbing damage created by a surge voltage process, and the discharge arc will cause the vaporization of the dielectric and metallization. After the arc, the insulation is restored, but an area of metallization is lost. You can see the corrosion damage in the top image, as well as the self-healing damage in the bottom image. The very white spots is where the arc happened, or in this case, many arcs. Partial discharge and oxidation process also can impact, but they have a smaller impact and are very reduced by the plastic casing and hermetic sealing of the film capacitors. So let's look back at the capacitive power supply. In the right, you can see the formula that defines the output current and thus the final power capabilities of the DC converter output. As you can see, it will change proportionately with the capacitance of the input capacitors. So if the capacitance drops over time, the voltage, the converter may not be able to supply enough current and the load to the load, and the voltage will collapse. We don't expect any other parameters in the formula to change. So voltage, resistance, frequency, everything will remain. So we can say that a stable capacitance, is very critical for this application. In the curve in the right, you can see in the left, you can see the performance of such a converter with different capacitors. For the reasons we explained before, we only specify X2 capacitors for the application as interference suppression capacitors between L and N across the mains voltage. This is the notice that you should find in the datasheet of one of the regular FTX2 capacitors. Please, if you are not sure about having the right capacitor for your application, contact us. So to finish the session, I will give you a brief overview of what we learned in this webinar. First, we saw what happens to different capacitor types under temperature and humidity conditions. Then we look into detail of film capacitors and different types and applications. Finally, we spoke about what the consequence of harsh conditions on film capacitors and on the different applications. Before I finish, a suggestion from my side, maybe you are already familiar with REDEXPERT, our online component selection tool. You can find it easily in our website or also in our online catalog, and it's completely free to use. You don't need to register, but if you do, you can use more functionality like moving the sliders. To get the values at certain points, like the impedance at 30 kilohertz in this example. You can also select and order free samples with one click. In the presentation, I have shown some graphs that have the REDEXPERT logo on them. So that means you can find those graphs in REDEXPERT. Marcos?
Yeah, so thank you very much, John, for your interesting presentation. Yeah, so now we would like to turn our attention and turn your attention to our question and answer session. So we wait until we get some questions, but I see we also already got in the meantime of the webinar also some questions. So just the information before we start into the questions for you. If we don't have the time now in the live webinar to answer all your questions, we will answer them via email after the webinar. And if you still have any other questions left after the webinar, just email us at the shown email addresses. So Yeah, then let's start. John, I see the first question. So how to protect the capacitor from humidity and moisture effect?
Yeah, thanks, Marcus. Yes, good question. It depends on the application. Of course, if there is moisture, and this is, I mean, if we have liquid on the board, we may be it, we may be having issues with other components before we have problems with the capacitors. But we don't recommend to use coating or potting, but it may help. And in the case, the best solution is to use the right component, the right capacitor. In this case, a THV film capacitor should perform fine, as I explained in the presentation.
Okay, thank you very much for your explanation. So then let's go on to the next question. So can a Y capacitor be used as an X capacitor?
Yeah. Yes, it can be used for an X capacitor. So that's the short answer. Normally, it's not a very practical solution, but it's possible. There is nothing that speaks against it, and normally every Y capacitor have a rating for X for an X connection. The only issue is that normally Y capacitors have, because they have a thick dielectric, they will be bigger for the same capacitance values, and maybe will be different to find the correct capacitance as the X capacitor.
Okay, then let's go on with the next question. Why is X2 is not recommended for a cross-domains application? Cross-domain application.
Yeah. Yes, I explained. I think the question maybe came before I explained it in another slide. Yes, as I said, as the capacitance drops with time, it may not be able to handle the converter will not be able to handle the power. So it will not. Yeah, it will stop working. So it's very dependent of the capacitance being stable.
Okay, thank you very much. So then let's go on with the next question. THB test is only required by safety capacitor, or is it also required by DC link or LLC application?
It's a very good question. So it's it could be. I mean, these components are especially made to be THV capable. So it's not it's not only the test, but also the capacitor must be. It's a special manufacturing process. So it's possible, but I don't think there is such demand for that. And for sure, we are not going to. We don't have this in our portfolio for now, but I guess it's possible to have the same in DC Link or other applications.
Okay, thank you very much. So then as we have a look at the next question, also just the information from my side, you will also get the link to the presentation as well as to the recording of this webinar only in the next few days. We will send you therefore an email. So then let's go on, John, with the next question. For the THB film capacitors, are there any change to the metallization to resist corrosion?
As far as I know, no. The corrosion is I think is happening always because the moisture, some water vapor, it's trapped inside the casing, and in the case of regular film capacitors, it's also permeating the walls of the plastic walls of the capacitor and going inside and corroding. And then THP capacitors, they will be manufactured with that in mind, so they will be filled better and they will be more hermetic. And the only way to resist the corrosion is just not to have this humidity inside. So as far as I know, the corrosion is always going to happen when the vapor is inside.
Okay, thank you very much. So then next question. For those capacitors robust to TNH, you mentioned some 1% decrease in capacitance per 1000 hours. What will happen for the next 1000 hours?
It's very difficult to make predictions in this aspect. This is why we do harsh test, accelerated test, to do so that we can make predictions of longer time in not so harsh conditions. In this case, I don't know. We had a very good result. Actually, up to 10% decrease was acceptable for us. But we cannot know if after 1,000 hours more it will break down or something. So in this case, for these specific parts, I can expect another 1% decrease, but it's very difficult to say.
Okay, thank you very much. Then let's go on with the next question. Is there a one-to-one replacement for those new THB types?
Yeah, good question. Yes, this will be possible for some parts. Of course, as I said, the manufacturing process of THB is a bit more robust, so the walls of the casing may be thicker and the dielectric. So it's possible that the components are a bit larger, but sometimes depending on what is mounted close to the capacitor, sometimes it's possible to have it in the same size, just 1 millimeter wide or 1 or 2 millimeters higher, and sometimes it will not be possible because they will be larger for the same capacitance value.
Okay, so I think then regarding just time, let's go on to the next and last question. So John, what is the construction to prevent failing open?
As far as I know, it could be a double isolation. So the layers of electrode and dielectric, they are organized in a different way to ensure that that the failure will happen open. But to be honest, due to the self-healing property, they always fail open because normally they self-heal and the dielectric will be rebuilt in the spot. But this happens also to X capacitors. Y capacitors, to assure that this is also going to happen, they have this, as I said, this double isolation. So you can imagine it being two capacitors in series.
Okay, so then thank you very much for your explanation. Yeah, so now we are already finished with our webinar. I see there are some questions left now, so we will answer them later on via email. So thank you very much for your attention, and I hope you enjoyed our webinar. Also, many thanks to you, John, for your time today.
Thanks, Marcus.
So then I hope you will hear us at our next webinar, and I wish you a good day. Thank you and have a good day. Goodbye.
Goodbye. Bye.